Good morning, everyone. Welcome to the UTIG seminar. And this morning, I'm really delighted to welcome and introduce Alice Turner, who is a UTIG institutional postdoc who joined us earlier this year. So Alice is an expert in earthquake rupture mechanics and earthquake source seismology, and she's done work on both Earth and the Moon. And that was done as part of her PhD at the University of Oxford. And also as part of her master's degree in geophysics at the University of College London. So she's going to be telling us about her work, I believe, as part of her degrees, and then also her work here at UTIG. And in addition to all of the great research, she's also involved with community service and outreach activities. And I'll just give one community service aspect, which she's co-organizing a new planetary science reading group that's integrated across the whole campus. So that's been a really great thing that just has been started by Alice. And I'm really looking forward to your talk, and I'll leave it to you.
Thank you very much. Thank you everybody for coming this morning. And before I start, I'd just like to acknowledge everybody who's helped me on this. So Jess Hawthorne was my PhD advisor, and then obviously Sean and Daniel while I'm here at UTIG. Oh, I have a clicker. I don't have to stand by the computer. This is amazing. So just as Krista says, I am an earthquake source seismologist, which basically means that I use the wiggles that we get on seismometers to try and understand things about earthquakes. And in the past, I've looked at things like repeating earthquakes in California. So this is a weird problem because repeating earthquakes, we should understand them. They're a nice simple system, but they seem to happen less often than we think. And so in this project, I was looking for little earthquakes that are happening in the same place to see if that could explain some of the seismic budget, but it didn't really. And then during my master's, I was looking at deep earthquakes. And this is really interesting because they're happening at really high pressures and temperatures where we don't really expect earthquakes to happen. So I got some new measurements of the durations and the sizes of deep earthquakes, and they seem to behave more like shallow ones than we were expecting. But that was kind of some stuff that I've done before. But today I'm going to be talking to you about moonquakes, things that I did during my PhD, but also since I've been here. We're going to start off with kind of some background on the Apollo seismic instruments, and then I'm going to talk about two different types of moonquakes, deep ones and shallow ones, and I'll wrap up with some kind of fun ideas that I've had about moonquakes going into the future. So first off, how do we even know that there are moonquakes? So during the Apollo missions, 4 seismic stations were all placed on the near side of the moon. And you can see that they kind of make up this equilateral triangle with the spacings between the 4 stations about 1,000 kilometers, except obviously for the 2 that are in exactly the same place. And these seismic instruments operated for 7 years in total before they were unceremoniously turned off at the end of the fiscal year in 1977. But it's still amazing. We have 7 years worth of data that was recorded on the surface of the moon. And I think there's just some things that I would like you all to bear in mind while we're talking about the signals that were recorded using these Apollo instruments. The thing to remember is they are old. And they are very different to modern day seismometers that, if any of you have any experience with, are just a whole different kind of kettle of fish. And so you can see in this figure here, this top one with the red, green, and orange lines, this is the frequency response of an instrument. So it's basically telling you how good an instrument is at measuring different frequencies. And the red line on this very top figure is of a modern day instrument from Albuquerque. I just picked a random one. And you can see that it has a nice flat line across a big range of frequencies. And that's what we want. But you can see in the orange and the green, these are 2 different modes that the Apollo instruments operated in. And they're not nice and flat. And you can see even specifically, this orange one here has like a peak. And that means that frequencies in that kind of peaked area are amplified relative to other frequencies. And so that's something that we have to bear in mind. These instruments are not perfect modern day seismometers. And the other thing is that the data had to be sent back to Earth, and it was encoded in 7 bits, which means that sometimes when the noise is really low on the moon, which it is quite often because we don't have people stomping around driving cars, no anthropogenic noise on the moon, you basically get down to the digitization level of the instrument. And so you get stuff that looks weird and like this. So just bear in mind, the instruments are a little bit old. And so now how the data was processed originally. So when I started my PhD, I had to look up what a magnetic tape looked like, because I had never seen one. And this is what all of the original data was stored on. And then the data was obviously processed from there. And ideally, we would have liked to have some sort of automated way to look at all of this amazing data, but it turned out that that was really hard. And so there was so much care and detail was gone into picking the original data, which was then stored on more tapes, but this time with the seismic events picked out. But luckily for me, I never actually had to deal with any of these magnetic tapes. There's been a huge amount of effort to preserve this data, and it's now available on the IRIS website for you to just download however you want. And so I think that we just have to say thank you to everybody who was involved with preserving this data and making it available to anybody who wants it, so that people like me can come along 50 years later and look at this data, and I don't have to deal with all of the difficult things of getting data off of magnetic tapes or whatever other format I had never heard of before. And so I think now is a time to acknowledge that we're in a place right now, sitting here with a long history of this Apollo seismic data. And so Constantino wrote an article about this a couple of years ago, which you could go ahead and read if you would like. But basically, yes, Yoshio Nakamura has been working on the Apollo data since basically the beginning, and here at UTIG, and we definitely wouldn't be in a place where we are today, where young people like me, if I'm allowed to call myself a young person, I guess maybe I'm older now, can still go ahead and make amazing discoveries with this data, even though it's 50 years old. So yeah, take a moment to be happy about history, I guess. Anyway, enough on that. We're now going to talk about the actual signals that were recorded during this 7-year lunar seismic stations. So there were 4 kind of signals that I'm going to talk you through: shallow moonquakes, impacts, deep moonquakes, and thermal moonquakes. But before we go into talking about each of these individually, I want you guys to just have a look at these signals. So here you can see that there are 2 figures for each of these different types. And that's because at each seismic station, there were 2 co-located instruments: a short period instrument, which is kind of more sensitive to higher frequencies, and a mid-period instrument. And we can see that actually, regardless of which component you're looking at or which kind of type of signal you're looking at, it looks kind of fuzzy. You can see there's a long ringing coda in all of these events. And this is basically because the surface of the moon, when you look up at it in the night, you can see all of those craters on the surface. And that has meant that there's loads of fractures in the top layer. And when you get any seismic energy traveling through, it's bounced in all sorts of different directions. And so that means that it can take up to an hour to arrive at the seismic station. So the seismic coda, which is what we call this kind of long ringing train of energy, can last up to an hour, which is a lot longer than it is on Earth. this actually is one of the things that makes doing moon seismology compared to Earth seismology a little bit difficult, because this coda can hide some of those arrivals that we really, really want to see. So on Earth, you're looking for your P arrivals, your S arrivals, but I think maybe you guys can agree it's hard to see any sort of phases in this big kind of random jumble of energy. So we're going to kick off with thermal moonquakes. So these are very small magnitude, impulsive events that happen very close to the seismic station on which they were recorded. And they're basically the moon's response to temperature. So because the moon doesn't have an atmosphere, the temperature variation between day and night is very extreme. And then the rocks expand and contract, and you get this little signal. And so you can see on this bottom figure here, we kind of have like a twice monthly peak in the number of events. Just moon gets hot, moon gets cold. And so this top figure here is from a paper that was published fairly recently, actually. And you guys might have seen it. It got picked up in the newspapers quite a lot. And so in this paper, they were using machine learning on the Apollo 17 geophones to identify some of these thermal moonquakes. And you can see here that they've identified kind of 3 different shapes. So there's this more impulsive event and then a more emergent event. And they suggest that one of these types is actually related to the lander getting hot and cold. They were able to localize it. So lots of the news articles were like, stuff left on the moon is making moonquakes, which was kind of quite sensationalized. But yes, so little thermal moonquakes is one type of event. The next type of event is impacts. So anytime anything hits the surface of the moon, we can record that shaking. And the example here is from when we purposely went and hit something onto the moon. So the Saturn module was crashed into the surface, and you can see in imagery that impact, and we were able to record it on the seismometers. But it's not just things that we purposely crash into the surface of the moon that you can see. You can also detect natural impactors. So anything that's making a crater on the moon, you could detect with seismology. And then we're coming on to the type of moonquake that I'll come on to discuss later, which are shallow moonquakes, which are really weird. They are the largest type of event that was recorded during the missions. They have a kind of an equivalent body wave magnitude of 5.5. So that's pretty big. If you were standing on the surface of the moon, you'd definitely be able to feel that. There was an estimate they had a stress drop of 100 MPa, which is really high. So compared to earthquakes, they normally have a stress drop of between 3 and 10 MPa. And the weirdest thing for me is that there's only 28 of them in the original catalog. And people like to correlate these with surface scarps. So you can see this figure here, all of the red dots are kind of scarp features, and then the blue circles are the moonquakes. And we go, okay, if the moonquake is shallow, maybe it should have something that we can see on the surface. But if that is the case, and they are a tectonic feature, why are there only 28 of them? And why are they all pretty big? Wouldn't we expect to have a more Earth-like tectonic thing where you have lots of small shallow moonquakes and fewer big ones? So in conclusion, shallow moonquakes are a bit weird, but we'll come back to them later. And for now, I'm going to talk about deep moonquakes. So deep moonquakes are happening between 700 to 1,200 kilometers inside the moon. That's roughly halfway between the surface of the moon and its center. And you can see here, there's a bunch of red dots showing the locations of these deep moonquakes. But actually, each of those dots isn't just one deep moonquake. It's a location where deep moonquakes are happening over and over again, which I like to call, or people like to call, nests, which is a very cute name. And in these nests, these repeating deep moonquakes have a tidal periodicity, which basically means you get a deep moonquake about once a month. So you're like, okay, problem solved. Deep moonquakes are caused by the tides. But then you have to remember that this is happening 700 kilometers inside the moon, where the tectonic stress really isn't very big. So then maybe there are some other stresses acting inside the moon that can help trigger or drive deep moonquakes. So the question that we're trying to answer is, what stresses drive these deep moonquakes? Is it just the tides alone, or is there some other tectonic stress deep in the moon that we don't know about? And just to be clear here, when I say tectonic stress, I just basically mean any stress that isn't tidal. Haven't really, we can think about what it is later, but just anything untidal. And so why are we interested in the stresses that drive deep moonquakes? And this comes back to this idea that they're happening at really high pressures and temperatures deep inside the moon, actually quite similar to intermediate depth earthquakes in subduction zones. So we have all of these same problems of we shouldn't be getting frictional behavior, but we do. So we need some kind of model or mechanism to explain it. And up here, you can see in this figure there, these are just a couple of different models that have been used to explain intermediate depth earthquakes. And so the question is, well, if it's the same pressure and temperature conditions, is maybe a similar mechanism working inside the moon? So the first one up here we have is, could a phase change be causing some stresses? Maybe. This second one is thermal runaway. And this is basically where you get a little bit of slip and the fault will get hotter, and then it will get weaker, and then it will slip more. And so you get this runaway process. We could have some increased pore fluid pressure. So fluids can reduce the effective normal stress, which might be able to make our fault slide at really high pressures and temperatures. Or maybe something about the kind of fault itself that's making it very weak. But to be able to answer anything about which mechanisms could be causing deep moonquakes, we first need to know what stresses are. And so to answer this question, I use a type of deep moonquake that seems to have a reversed direction of slip. So our deep moonquakes that are happening in the same place over and over again have the same waveforms. We can match them up. But there were some that seemed to be identical, but just flipped. And so you can see that here in the green and the blue waveforms. They look the same, but one is just kind of flipped relative to the other one. And this suggests a reverse sense of motion on the fault. And so we have two models to explain these reversed polarity waveforms. In our first plug model, we have a really large tectonic stress that is always pulling in one direction. And in that case, we can imagine that this force is pulling a plug of material. And in that case, we get reverse sense of motion on either side of the plug as it's being moved. So our blue and our green waveforms will be separated in space. In our second model, we have a large tidal stress. The tidal stress can just change direction as it likes. And in this case, the green and the blue waveforms will be separated in time as the fault just kind of changes the direction that it's moving. And so we want to be able to tell the difference between these two models using observations. And to do that, we note that in our first model, the plug model, where we have two different faults either side of this plug of material, the slip direction, the direction that the fault is moving, is always only forwards or backwards. So we just have one slip direction with a reverse sense of polarity. Whereas in our tidal model, the fault can slip in any direction that it likes. And so we have, to explain this, we would need two slip directions. So to describe the motion of the fault, we can use any combination of forwards, backwards, left, and right. And so now we want to make some observations of the directions that the faults are slipping. Is it slipping always in one direction or two directions? And to use this, I use the principal component analysis, which is kind of a normal statistical technique. And it's basically used to look for a new basis function of a bunch of data. And we're just applying it to our waveforms. And so you can, I'm going to kind of try and throw out a couple of different ways of thinking about this, because it can be a little bit hard. I find it hard to conceptualize. So one way is this thinking of it as a basis function for our waveforms. And so in this case, we have a bunch of observations, and we're asking how many kind of basic waveforms can we use with different weights to recreate our observations. And so in the plug model, we would only need one basis function to recreate all of our observations, because it's only either slipping forwards and backwards, and the weights would either be in a positive direction or a negative direction. Whereas in our tidal model, we would need two components to represent that: forwards, backwards, left, or right, and then each of these observations could have different weights. So that's one way of thinking of it. And the other way is maybe we're just looking for the signal that is common amongst a bunch of different signals. And we can then equate that to slip directions. And so in our plug model, we would just have one thing that's common to all of the signals, and the rest is noise. And in the tidal model, we would have two things that is common to all of our signals, and the rest is just noise. But anyway, the important thing to take away from this is plug model, one thing looks like a moonquake and the rest looks like noise. And in the tidal model, two things look like moonquakes and the rest looks like noise. And so this is what we get when we apply the PCA to a bunch of signals. And so on the top, you can see here are the moonquakes. And on the bottom is what you get when you apply the principal component analysis. And so you're always going to get the same, when I apply this, you're always going to get the same number of principal components as signals that you put in. And so the game that we're trying to play is how many of them look like moonquakes and how many of them look like noise. And so you can see here that the first two look a bit more moonquakey. They have kind of an arrival and a coda, and the rest of them just look a bit like random noise. And so by just looking at this, we think, okay, there's two of them, that's two slip directions. But we're not totally convinced by just looking at stuff, and we want something slightly more robust. And this is where we're now going to focus on, instead of looking at the principal components themselves, we're going to look at the weights. So how much of each principal component do we need to explain an observation? And to do this, what I do is I take out one moonquake from my data set. I recalculate my components. And then I'm going to project my left out waveform onto the component. And that will give me a measure of how good that component was at explaining that piece of data. And so then we have a measure of how well each moonquake can be explained with our analysis. And we get a slightly confusing figure that looks like this, but I'll try and walk you through it. And so if we start, the thing to remember about this is if a component has a non-zero value, it means that it's contributing something to explaining our data. Whereas if it has a zero value, it's not doing anything. It's just noise. It's not adding any useful signal. And so the top histogram shows the weights for the first component. So that first one that looked like a moonquake that I showed you on a couple of slides back. And you can see that these weights have a distribution that is not zero. So that means that it's probably explaining signal and not noise. We can then see on the histogram, the first histogram to the left, I can use my pointer and show you this one. You can see it's slightly less clear, but we definitely have our two peaks away from zero. And so that means that it's containing signal and not noise. And then lastly, we have these two bottom ones, which are the third component and then the last component. And you can see that these have their weights concentrated around zero. That means that they're not really adding any signal to they're not signal. And so this means that we have two components that are not noise, and the rest of them are just noise. So this slightly more robust quantitative analysis is also suggesting two slip directions. And then finally, we're going to go back to looking at our components again. So those blue wiggles that I was showing you before. And we do some bootstrapping analysis, which is basically when you take different subsets of the data, recalculate the PCA, and look at what you get. And the idea is that if something is robust, if it's signal, then it will be the same every time you do it, regardless of what data you use. And if it is just noise, then it will look different each time. And we can pull this out using clustering analysis. And so you can see here that when I've applied my clustering algorithm, we get two blobs, a blue one and an orange one. And so that suggests that there were two things that were common among all of our bootstrapping and looked the same, so they're likely to be signal, and the rest was just noise that looks different every time. So this third line of evidence has suggested that there are two slip directions. So finally, we can come back to our models, and we can remember that the tidal model is where the tidal stress is larger than any other stress, and the fault can slip in any combination of left, right, up, or down. And this was two slip directions, and we observed two slip directions. So these observations are suggesting that the tidal model is better at explaining what we see. And so this suggests that the tidal stress alone is the thing that is driving these deep moonquakes. And then we can come back to our models of what is causing deep moonquakes. And so just because the tidal stress is larger, it doesn't mean that there's no other stresses acting. We can just use it as like an upper limit. And so we have a modeled idea of what the tidal stress is, and that's 0.1 MPa, which is pretty small, which is around 1 bar, I think, for the conversion. So any other stresses acting at this depth of deep moonquakes has to be smaller than that, which is pretty small. And we can think about our models. And for this thermal runaway model, which is where the fault slips a little bit and then it heats up and then it gets weaker and it can slip more, you need some initial big stress to get that first slip that starts the runaway process. And modeling of this thermal runaway suggests that you need something a lot bigger than 0.1 MPa to start off this runaway process. So maybe that means that we can rule out one of these possible mechanisms for deep moonquakes. And then we can think about what we're left with of a phase change. Seems unlikely. That's something that's much more common in subduction zones where we know what's going on, or increased pore fluid pressure. Where's the water on the moon? If it's not water, is it melt? So you're left with all of these weird questions about what is the mechanism of deep moonquakes, but it's probably not thermal runaway. So I'm just wrapping up this little section on deep moonquakes. And so we used the principal component analysis to try and understand if there was one slip direction or two slip directions. And because we found two, it suggests that deep moonquakes are driven by the tidal stress. Okay, nice. So now I'm going to move on to, that was all work that I did during my PhD. And now I'm going to move on to the stuff that I've been working on since I got here at UTIG on shallow moonquakes. So shallow moonquakes can look quite similar to impacts. And I'm going to leave this slide up for a minute so you guys hear. Again, we have the short period and the mid period. And so two of these signals, and they're stacked. So the two top rows are one component or one instrument, and the two on the bottom row are different. I want you to try and think about one set is an impact and one set is a shallow moonquake. And so have a think in your head about which one you think is which. And I did this at a poster at a conference just this week, and everybody was surprisingly good at it. So I think you guys can get it. Okay, I'm going to reveal the answers now. So on this side was the shallow moonquake. On the other side was the impact. And maybe you can kind of see some differences, but mostly the point I'm trying to make is they look pretty similar. And so it can be pretty hard to tell the difference between a shallow moonquake and an impact just by looking at it. And so we would really quite like to know what's an impact and what's a shallow moonquake, because that tells us the seismicity rate of the moon. And also personally, I think it would be really interesting because, as I mentioned at the beginning, there's only 28 shallow moonquakes, which is a bit weird. And so if we're looking for new ones, if we think maybe there's only 28, they are tectonic, but we're just missing a bunch of them. So maybe we need to go out and look for more. But part of looking for more is actually being able to tell what is what. So we want to be able to tell what is seismicity and what is just an impact. And then the other thing is that there is going to be a new seismometer taken to the far side of the moon for the very first time as part of the PRISM CLIPS NASA, where they take a commercial lander and put some instruments on it. And this is going to be the most sensitive instrument that is ever operated, most sensitive seismometer that has ever operated on the moon. And this far side seismic suite has a bunch of science goals, which you can kind of see summarized here in a figure that I've taken from Mark Panning. But we still need to be able to tell what is a impact and what is a shallow moonquake. And so we want to kind of come up with a better way of telling the difference that doesn't require us to just look at signals really hard. And so that's what we're trying to do. We're trying to use some statistical methods to identify the difference between shallow moonquakes and impacts. And I have used two different methods to do this. And I'll start off with using the KL divergence. So the KL divergence is another statistical method that can be used to tell the difference or tell you how similar any two distributions are. And basically, the idea is that if you give it two perfect distributions, the KL divergence will be 0. And so the lower this value is, the more similar the two distributions are. So sounds great, a nice way of being able to tell if things are similar or if they're different. So the first thing that we have to do is we have to make a moonquake look more like a probability distribution. And the way that we've done this is by converting it into this different way of looking at it. So the bottom axis here is still the time, so the same as the waveform on the top. But now instead of the amplitude, we are looking at the frequency. So you can basically think about this as the frequency content in each little time chunk. And then to make it definitely look like a probability distribution, this figure that I'm showing here has been smoothed and normalized. So yay, now we have something that looks less like a moonquake and more like a probability distribution. So we can go ahead and compare all of our different pseudo probability distributions of moonquakes to each other using the KL divergence. And you get something that looks a bit like this. And so I have the KL, this is plotting the KL divergence for a bunch of different events. The ones plotted in blue are impacts compared to shallow moonquakes. And the ones plotted in orange are shallow moonquakes compared to other shallow moonquakes. And so you can see perhaps these orange ones are a little bit lower. They have a lower KL divergence when you compare a shallow moonquake to other shallow moonquakes. So shallow moonquakes are more similar to each other than they are to impacts. But there's one blaringly obvious one that doesn't fit with this. This guy just here. And so we're going to have a look at this one. So I went in and I had a look at the data for this event. And you can see that it has a bunch of these vertical lines on it. And these are spikes. They're very common in the Apollo data. It's just the instrument had a bit of a tiz. It wasn't happy. And normally we do some pre-processing to get rid of these. You can do a median average filter that removes some of these spikes. And apparently on this one, I did not do a very good job. And so that's why it's like, guys, I'm not like other moonquakes. And it has a much higher KL divergence, telling us it's very different. So this has highlighted the importance of pre-processing. But hang on, I'll just go back to, oops, wrong way. But you can see that this isn't a perfect way of separating the shallow moonquakes from the impacts. We have a lot that are kind of falling around this line that separates them. We have one that's just above a line and a bunch of the blue impacts that are very close to the line. So we want to try something that maybe does a little bit of a better job. And this is where I've been using a Python package called tsfresh. I will pause for a moment to tell you how much I love tsfresh. It is amazing. If you do anything with time series, I recommend it wholeheartedly. Basically, you give it a bunch of time series and it will give you thousands of features back. And so it can give you simple things like the maximum, the minimum, the number of peaks, the median, but it can also give you more complicated things like the Fourier coefficients or the autocorrelation, and it just dumps them all at you. And another nice thing is that if you give it two different populations, so in my case, I'm giving it the impacts and the shallow moonquakes, it will tell you which features are significantly different between them. So brilliant, very easy to use. There's my plug. And so when I give all of my waveforms to this Python package, it says, okay, these are the ones that are different between impacts and shallow moonquakes. This is a bunch of writing, but it can basically be summed down to features that describe how similar the signals are to themselves, so the autocorrelation, and then a bunch of features that describe the energy in the signal, which is actually very similar to what we were trying to get when we were looking at the probability distributions with the KL divergence. And so here I've just plotted an example of two of those features. So this is the autocorrelation, and then this is, which is one of those measures of how similar a signal is to itself, and a Fourier entropy, which is a measure of the energy. And you can see that our shallow moonquakes plot up here, and the impacts are down here. So they're plotting in different places, and we're managing to separate them out. Yay, that's what we wanted to do. And so finally, we can pull all of this together. So we had 6 features from the tsfresh package that were different between impacts and shallow moonquakes. And then we were getting some information from the KL divergence of the things that were different. And so here, this is just, that's 7 features. And I want to look at them all, but I can't visualize 7-dimensional space in my head. I don't know about you guys, but I'm not very good at it. And so I'm using this algorithm called TSNE, which basically takes 7-dimensional space and squishes it down into 2 dimensions so we can look at it. And so things that are similar in 7 dimensions will plot close together in 2D. And so we can see here that our impacts in blue are over here and our shallow moonquakes cluster over here. So this is showing that maybe there are some statistical things that we can use to tell the difference between shallow moonquakes and impacts. But obviously, I'm not done yet. And some really exciting things is that there is another postdoc, Odinera, who has actually just started in Paris, who thinks that he has found some new shallow moonquakes. And so that's taking up the 28 that we had in the original catalog to a much bigger number. And I'm really hoping that I'll be able to have a look at his new shallow moonquakes and see where they plot on my almost phase diagram of seismic impacts or shallow moonquakes, and add to those orange dots that I have on my figure to kind of just get more data points, because we don't have very many shallow moonquakes. So I'm hoping to do that next week. And I'll just kind of give a little summary again of this shallow moonquake stuff. I was trying to tell the difference between shallow moonquakes and impacts using statistics, and I think I have. They plot in different places. And so hopefully this will be a useful tool to think about the data that we already have, but also as an automated tool for any new data that we get from the new instrument that's placed on the far side of the moon. So before I wrap up, I just want to talk a little bit about some fun ideas that I have for other things to do on the moon. And so this is coming back to our deep moonquakes and thinking about this mechanism. And is there so we've ruled out thermal runaway because the stresses aren't large enough. So is there anything we can do with the current data to inform us about any of these other models? And so I've highlighted here this model of a smooth fault. And so this is the idea that because moonquakes are happening over and over again, they might have ground down the surface of the faults. And if they're really smooth, it will be easier to make them slip. They'll be weak. And then maybe we don't need a big stress to drive them because they're just so easy to slip. And so what can we do to try and test this? On Earth, we can explain, people like to explain faults using kind of a rate and state framework. And so the idea is, can we use this rate and state frictional framework to try and describe the occurrence time of deep moonquakes? And you would just fit it with a proxy for this really smooth fault, making it really, really weak. The idea is, if we make the faults really, really weak in our model, can we make them slip with just the tidal stress? And so that's what I'm hoping to work on soon. And then finally, my final thoughts. It's an exciting time to be working on the lunar seismic data because we're getting a new instrument. And everybody who's works in planetary science is always excited when you get a new instrument or a new mission. And this is going to be amazing. It's going to be the first recording on the far side. And it's going to be like a million times better. It's a modern instrument that's being placed on the moon. But I want to say that the Apollo data is still going to be an amazing resource, and it's going to still be really, really useful. So firstly, there were 4 stations, not just 1. And the other thing is that a lot of the challenges that we have with the lunar data is related to that kind of scattering long coda that we have. And that's not going away. The moon is still going to be the moon, regardless of the instrument that we put on there. And so it's not like that the Apollo data is going to be really useful in kind of figuring out what we're going to need to do for the new data. So that's all I have, and thank you very much for listening.
Great, thanks, Alice, for the great talk. Are there questions?
Hey, great talk. I was wondering, for your impactor-induced moonquakes, is there any minimum impactor size, or are you because I assume there's a lot of like micrometeoritic impacts, and so are these mostly large impacts or kind of the whole spectrum of them? Do you have a cutoff of what you're saying, yes, this is a big impact or an actual impact?
Yeah, so I think that it's perfect we're on this slide. This is actually a big goal of the far side seismic suite, is to get that noise level down low enough that we can get the micrometeorite impactors. And so I think that I'm not sure, I haven't looked a lot of this, but I think most of them are maybe slightly larger for the Apollo data because we had a slightly higher noise floor. And so hopefully with the new instrument, we'll be able to get the noise floor lower down and see the smaller impacts.
I see that Sean has his hand raised. Maybe we'll do there, and I'll pass the microphone to the next person in the meantime.
Great. Awesome talk, Alice. I just had a quick thought or a quick question, which is, could you comment a bit on using a single station such as the new Farside Seismic Suite, or using InSight on Mars relative to, in the future, seismic networks? What is that going to do to help us differentiate shallow quakes and impacts?
Yes. So I think that InSight has showed us that one of the really hard things about using just a single station is finding locations. And so obviously locations is useful, especially if you were looking at these shallow quakes and you were trying to correlate them with surface features. And on InSight, they have been using phases to try and do that. So the moon is a lot less the Mars is a lot less scattering, and so they have some phases to try and do some preliminary locations. And then on the moon, we're just lucky that we have the Apollo data, and so we have some idea of what to expect. And so I think that you can see that the signal characteristics between a shallow moonquake and a deep moonquake can be quite different, and they have different frequency contents. And so even if we don't get a perfect location, we do have some kind of idea of what class these signals will fall into based on what they look like. But getting accurate locations is probably going to be one of the big challenges of just having a single station on the highly scattered moon.
Great, thanks.
Great talk, Alice. I have a lot of questions, so just I don't even know if I'm gonna remember all of them. So when you define this deep moonquakes, you define them as a fault zone. You say there is a surface or something like that. So, and you say they always happen in the same place.
Yes.
So, and you have data for 7 years,
Mhm.
but there's nothing that says it didn't happen for 1,000, 2,000, 100,000, millions of years.
Mhm.
So if these structures are constant over time, at least on some thermal timescales, you know, like a cooling of the, you know, at some smaller thermal timescale than the life of the planet, the geometry must be pretty special. I mean, it's like in a sphere, when you you squeeze it and expand it and squeeze it and expand it, you should get some sort of, and it's pretty homogeneous. You should get some sort of geometry that is, you know, regular. I mean, you know, it's a geometrical problem. Did you think about that kind of stuff, or?
As so you're asking if there's any kind of geometrical control on the location of the repeating earthquake nests?
Yeah. If there is a geometry for all this, you know, fault zone that repeats and repeat and repeat.
Yeah, I think that I guess if you're asking like, would you be able to tell the strike and the dip based on?
Oh, no, it's worse than that.
Worse than that.
I'm asking in the shape of a sphere, when you expand and squeeze it, you know, what kind of structure do you get in terms of faulting, you know?
Yeah, I think so. The depth of the deep moonquakes between 700 and 1,200 kilometers is kind of linked to just the there's a peak in the tidal stress based on the composition.
Yeah.
So the depth makes sense, and then why they're kind of not everywhere, or why they're in these kind of like random little nests.
Yeah.
I don't know.
Yeah. Okay.
And
directional. Why?
Yeah.
Oh yeah, so I can answer that one. So you can see here on this figure that it seems the kind of deep dots here are the deep moonquakes, and they all seem to be on the near side.
Okay.
So maybe is that just because all of the stations are on the near side? And so if you had some sort of partial melt layer or something that's deflecting the signals from the far side, then you just wouldn't be able to see them if all of your stations were on the near side. But then you think about actually the two hemispheres of the moon are different. You have kind of like different surface features, you have different crustal thicknesses between the near side and the far side. So that's another one of the key questions that will be super easily answered with the far side seismic suite of, is it just an observational bias because all of the stations were on the near side? Well, put a station on the far side, and if you detect the same seismicity rate on the far side, then it was just some interior structure observational thing. Or if you don't, then you have something of like, oh, well, what thing in the interior is meaning that you get deep moonquakes only on one side?
Okay, and just one more question. You speak about this, you know, as moonquakes repeat on the same surface, it just becomes smoother and smoother.
Yeah.
But my intuition is, if you repeat the earthquake on the same place, you're going to generate a fault gouge with very, very small grains. So it's not a surface anymore. It's a thickness with some grains of, you know, composition, and, you know, certainly very, very small, I suppose. So does it fit with your idea of you know, mechanics for the frictional mechanism for initiating these earthquakes? You know, does it fit with rate and state and all this thing?
Yeah, I think so. I was kind of basing this idea off of like mature strike slip faults on Earth that do seem to be slightly weaker than we expect them to be. So kind of the San Andreas fault. And I think that it's kind of like an ongoing problem about why that is. And you can get into complicated things about like, is it a pulse-like rupture? Is it a crack-like rupture? But I was hoping to kind of approach this in even a more simple way of just, so the smoothness is one way to explain a fault that's just really, really weak. And so if you kind of, that is kind of the bigger picture theorized, but the idea would just be model something that is weak for whatever reason, and see if you can get those occurrence times, because we don't even know, it might be, you would have to make it so weak that it's not even realistic under any ideas of, yeah. So they're kind of, the two things are slightly divorced from each other.
Great talk. Yeah, so to the extent that the earthquakes are caused by either shallow or deep earthquakes are caused by fault, I was wondering if Katie Aki's relationship between the kind of the average frequency of a wave and the size of the earthquake fault actually applies. And on Earth, it's a really robust relationship, logarithmic, but that in the sense that it is, if you have a really small event, then the fault plane is not much larger than this room, and et cetera. And I was just wondering, like, where these moonquakes fit in.
Yeah, so I think that for the deep ones, they seem to be about, in each nest, they seem to be about the same magnitude. So they are exactly the same happening over and over again. So they don't really fit into that distribution. But that is kind of similar to other repeating earthquakes that we see on Earth. So they kind of are an exception. So there's some mechanism that makes the same size earthquake happen again and again. Whereas for the shallow ones, that's what I want to expect. But I think the problem at the moment is that we just don't have enough events to see that distribution clearly. And I would like it to make sense, but it doesn't at the moment.
Thank you.
Oh, maybe just go to the online and then to Benjamin.
Okay, thank you, Alice. I really enjoyed this talk. I wondered, you talked about the catalog that these moonquakes come from and referenced at the end the sort of expansion of that catalog in exciting ways. I wonder, do you see your application of these kinds of statistical methods as having a potential for going back and being able to revise how that catalog is constructed and to use some of those techniques, not necessarily to, maybe to identify or to reclassify, or there's just an interesting this archive that you have and the way that it was sort of like once used and once looked at. Clearly there are so many new ways for looking at it today. Can you talk a little bit about just how that and then when you reclassify it, of course you could like reapply your methods. There's can you comment on how you see that working a little bit?
Yeah, so I'm gonna flick back a little bit. And so I have this figure here in another version of this plot, which I have not included. So in the catalog, events can be classified as, confusingly, it's put up as C here, which is impact, or H, which is shallow moonquake, but they can also be classified as Z, which is kind of, in the original catalog, it's a signal, but we don't really know what it is. And so I think there's a great opportunity to have a look at these kind of events where they weren't quite sure, and see where they plot on here. And I've plotted a couple of them, not very many, and they do seem to plot quite close to this kind of intersect, which is just going to say that, yeah, you were right for not being confident about what it is, because it does seem to kind of not quite fit our current duality. So I think that would be, going through some of these events that were kind of less, because I'm sure some of them will plot on one end or the other of the spectrum. But yeah, so it's definitely not just the new exciting events. We can also go back and think about what's in the catalog already.
Thank you.
So there's two questions in the chat. One is from Unikrishnan CK, and he asks, where is it? How important are surface temperature changes on moonquakes, and was there any systematic study?
Yeah, so there was that, I introduced in the beginning, there is this whole class of thermal moonquakes where the temperature is very, very important. And also the temperature changes for the instrument is also important. And so I think that's I'm coming back to the far side seismic suite again, but it's very exciting. And that's one of the challenges that they are really going to have, is that they have to have survive the night capabilities. So the seismometer needs to be wrapped up warm enough that it will still be able to operate throughout, and we'll get a substantial amount of data, because the risk is that the lunar day is only 14 days, and we want more than 14 days worth of data. So I think the temperature can have two effects. It can affect the moonquakes themselves in these thermal moonquakes, but it is also a big consideration for the instrumentation that we put on the surface of the moon.
And second question is from Freya Chen, and she says, thank you for the wonderful talk. I have questions on shallow moonquakes. Based on your classification, does that mean all shallow moonquakes have similar frequency contents? I'm wondering, what is your comment on their mechanisms?
Ooh, that's a really good question. So I think the KL divergence method was the one where I can most explicitly link between the frequency content and the events themselves, because I guess I spent a long time plugging the Python package, but it is a bit black box. You put it in and you get stuff out and you're not really quite sure why. And so I think that the KL divergence is really telling us that the frequency content of the shallow moonquakes is quite similar, and probably the trends that we see in the difference is related to the path that they took. And so as energy travels through the moon, the earth, anywhere, you get attenuation and bits get lost. And so the differences will be related to, we can say that they all started off the same, but depending on how far they had to travel, they'll be made different. And so yeah, the KL divergence is saying that mostly based on the events that we have, they do seem to have enough of their frequency characteristics in common for us to group them together. And then in terms of the second part of that question, which was, can you say anything about their mechanism? I'm scared. I don't want to make any assumptions. I think that currently at the moment with the events that we have, so firstly, I don't think this study particularly says anything useful about the mechanism. It's just a case of, can we tell the difference between them? And I think that at the moment, we can't conclusively say that they are tectonic. And so hopefully with more events, we'll be able to get that kind of event number distribution and their sizes, which will be able to go towards answering that question. So this is a step towards getting to the cause of shallow moonquakes, but definitely not all the way there. I hope that made sense.
Thanks. I have a question as well, kind of along those lines. So now that you've been able to distinguish between the shallow moonquakes and impacts, are there any spatial or temporal correlations between the shallow and the deep moonquakes?
Interesting. They're on this now. I think that the locations for lots of the shallow moonquakes are not amazing. And I can't think of any off the top of my head, except that they're all on the near side. But it would be an interesting thing to think about, that if they linked together.
Just a quick question, because you say they cannot be sensed from the other side. I'm not a seismologist, but you cannot detect if this is the source is on the other side, the far side, with the PKP kind of a signal arrival. That's,
well, I mean, this is just a random slide, but okay, on Earth, all of the phases are like nice and separated, and so you would be able to spot it. But it's probably somewhere in that like huge massive coda, and so there are a lot of kind of like super smart processing, stacking the signals, trying to bring out these coherent phases over the scattered signal, and that's kind of the techniques that they've been using to get measurements of the core size of the moon. But yeah, that's what you want, but it's really hard when all of your phases are kind of hidden and buried in the scattered energy.
okay. And last one, since you emphasized how old are the instruments, and they're probably highly sensitive to the clock that were made and timing, what your constraint on the uncertainties of the depth versus the new instruments that they're gonna deploy? You have, it could be 100 kilometer off than the actual 700, or?
Yeah, so there is a lot of uncertainty on the depth, and you're right that there was a lot of uncertainty on the timings. And so I think that a lot of the events don't have a good depth constraint. And so hopefully with the new instrument, you'll have fewer timing issues and you will be able to, I'm not exactly sure on the numbers of that uncertainty, but the issue is that it's a really nice modern new instrument, but there are only one of them. And so normally to get depths and locations, you need a nice, you need more than one station. Yeah, that's going to be one of the challenges of the new data is how do you get depths, how do you get locations with just a single station that doesn't have any nice clear phases.
All right, thanks. And before we officially thank Alice, I'd like to say that we're going to be taking her out for lunch. So if you'd like to join us, we'll meet in the lobby at 11:45. And with that, I'll say thank you, Alice.